Okay, guys, welcome to Unit 2. This is going to be about electrodes and shielding gases. So, hopefully, we remember some information from the first unit. Right, what polarity should we use for gas shielding? Just think about your MIG welding. It's going to be very similar to that. Why do we use a CV machine for FCAW? We should know that. Very obvious at this point. Any sort of wire fit process is going to require a CV machine, but we should understand why. What type of electrode is used in flux core arc welded, right? They call it a fabricated um, wire, but if you're looking at the actual classification breakdown, just like when we had the GMAW electrode, we've got that S, that ER70S-6, that's denoting the type of electrode. And so there's either going to be an S or a T there. So what does that T stand for? And then some terms we should be very familiar with at this point is CTWD, your electrodes stick out, and then the two acronyms that we're going to be dealing with, gas shielded and self shielded. All right, so let's get into it. So we'll be going over the different characteristics between self-shielded and gas-shielded electrodes, the different AWS classifications for them, and compare and contrast the shielding gases commonly used for flux core arc welding gas shielded, which is pretty easy. Typically, you're only on 100% CO2 or like a 75-25, like a generic MIG gas kind of mix. Very rarely do you ever get into like trimixes and things like that. Usually it's just argon and CO2. Okay, so T, tubular wire. Remember that that T in the AWS classification is tubular. Like we went over in the last unit, they form this into like a U-shaped channel, dump that flux inside of it, and then finish folding it into that tubular hollow wire. So elements inside the electrode, your flux, when melted, react with the atmosphere, producing a shielding gas, not unlike the SMAW process. Remember, you're always getting a little bit of that shielding gas right at the end of the electrode where all that flux is burning off. And also slag to protect the weld metal. Without some form of shielding, the atmosphere, the oxides and the nitrides from the atmosphere will get inside that puddle, produce gases, and will make that weld very weak. Okay, so remember those terms like deoxidizers. All right, that's pulling out the oxides. We also have denitrifiers, which pull out the nitrides, and those are cleaning out some of the atmospheric gases that you don't want inside that puddle. So the shielding flux allows for outdoor use. Again, very similar to SMAW welding. That flux helps not just shape the weld puddle, but also protects it from the atmosphere. If you're really good at watching that puddle when you're doing flux kind of based welding processes, you should be able to see that puddle, and then you should be able to see that kind of trailing slag behind you. Always looks like the puddle, but a lot darker. So keep that in mind. Pay attention to that when you're welding. Look at that puddle and see if you can notice the shape, the form of the slag that is trailing you. So heat from the arc melts the electrode and base metal to create the weld pool and slag. The process, all that heat going on, the thermodynamic process, helps force some of those dirty elements in the weld pool to the surface. And some of those additives inside the flux also help clean out some of those impurities, right? We call them scavengers or cleaners. So for gas shielded and self shielded, the electrodes are pretty much the same, just different sizes, different additives inside of the wire. Gas shielded flux is mostly filled with metallic and metallic oxide powders, so a lot of additives for like deposition rates and things like that, or cleaners. The gas shielded electrodes require that extra external shielding gas because they don't have near as much additives as like a self-shielded, and so you do not get that extra gas shield at the tip of your electrode like you would even in SMAW. So because they have less additives than a self-shielded, you're not getting that extra cloud of gas shielding, so you have to introduce gas shielding via a cylinder, so that argon or 100% CO2. So AWS 5.2 and 5.29, these are the AWS specifications. So your companies that make electrodes, that is the specification that they are trying to make those electrodes to in order for them to be classified under the AWS as that classification of electrode. Right, just like we've got SMAW electrodes, your E7018, they've got their own classification that manufacturers must reach. Lincoln calls theirs Excalibur, Miller calls them something different, but in order for them to be called E7018 E7018 or E6010, they must meet that AWS classification. And it's the same thing with our flux cord wire. And these are the AWS classifications that they must meet. So A20 and A29 for A20 carbon steel, A29 for low alloy steel. So getting into the classification system, just again, think about like your E7018, that's your AWS classification for SMAW electrodes, or your ER70S-6, that would be like your solid wire. Similar, a little different, you get a little more information, especially on the gas shielded electrodes. So we'll get into that right here. So E stands for electrode, first two digits indicate again tensile strength, so this should be familiar to you guys. Second of the two digits indicates the welding position, so first two digits 71, so that's the minimum tensile strength, 71,000 pounds. The second of the two digits, so that one, is going to be your welding position. Same thing as before, so you're only ever going to have a 1 or a 2 here, 1 being all positions and 2 being flat and horizontal only. Most all position welding electrodes can be used for vertical up and vertical down, all right, but some will not. Some of them it's only going to be a vertical down. Some of these flux cord wires have an excessive amount of flux, and so doing vertical up may be a little more challenging. The next letter after the second digit, that T, again, tubular. This is a tubular, also known as a fabricated wire. So that means if you have a T there, it's tubular. If it's an S, it's a solid. And the number after the T, so this 8 here, is usually usability and performance characteristics. So just like E7018, those last digit or last two digits is going to be your components and your flux. It's going to give it that kind of the characteristics of that specific electrode. That's kind of what makes that 7018, not so much the tensile strength or the fact that it's an electrode or the welding positions, but the characteristics, the flux components. That's kind of what makes that rod unique. All right, so that's what this dash number is going to be right here. So dash 8 would tell us, if we looked at a chart, all the components that are inside that flux. If a G is indicated instead of a number, so right here, if you have a G instead of a number, it signifies general classification, which is like a broad classification. If an S follows the G, so it might be a GS, that is designed for single pass welds only. Only single pass welds. So again, some of these wires, a heavy amount of flux or they're large diameter. Some of them are not meant for multi-pass welds. Some of them are meant for single pass groove welds. Think about like your sub-arc welders, how sometimes these things are meant to just have insanely high deposition rates so that you can eliminate the amount of passes you're trying to fill inside that groove. Some flux wires are designed specifically for just large single pass welds, not multi-pass welds. So that's what a GS would mean right there. So low alloy steels, their classification, you'll notice next to that T, or the classification itself is going to be like a T4, T67, T8, T11, TG, and for gas electrodes, T1, T5, TG. And this is kind of the broad classification of those electrodes. So you'll see this show up in like the code. If your electrode falls under like a T11, you'll get qualified for everything under it. So you would be qualified for T4, T67, T8, and T11 electrodes. If you get classified or qualified, in a T4 electrode, that's only going to be for T4. So the last designator, that H, your hydrogen, diffusible hydrogen level, just like on your SMAW electrodes, it's going to be the same thing. You're either going to have an H4, H8, or H16, and that is the diffusible hydrogen per 100 grams of weld metal. This ensures that metal will be low in diffusible hydrogen for crack-sensitive materials. So just like 7018 is a low hydrogen rod, you got to keep it in that oven to keep it clean, or to keep the hydrogen from absorbing in it, the hydrogen from the atmosphere. Because there's this thing called hydrogen cracking that can happen in certain welds. As you weld, you will trap hydrogen inside that weld puddle, and as it cools down, it's trying to escape, and it'll make weak spots. It might crack in those sections where the hydrogen was trapped inside, and so we want to keep hydrogen outside of the weld pool. So gas shielded electrodes, their classification, they've got a little more information on there. So after that dash number, you may see a C or an M, and that's going to tell you whether or not it should be used for 100% CO2 or a mix. All right, so that C right there, that's telling me 100% CO2 is what this electrode was designed for. And then you might have a dash J after that. That's an optional thing, and that's going to indicate improved weld notch toughness, also known as like impact toughness, so impact rating for that weld material. And then H followed by the numbers, the same meaning, so that hydrogen, diffusible hydrogen level. So a couple extra items for that gas shielding electrode, just keep that in mind. You're going to have that C telling you whether or not it's 100% CO2 or a mix, and then if it's met the requirements for improved toughness. So the electrode classification, the operating characteristics, right? That's going to be your specific polarity, your welding positions, the required external shielding gas, and whether or not it is a single pass or multi-pass welding. So these are characteristics of the flux component, that dash number, that is going to tell you all of this information. And then electrodes have usability factors, so this is more the flux components, right? Just like we've gone over in the SMAW module in 2A, different additives, different minerals, different components in that flux are going to give different characteristics to the puddle and the arc. Sometimes it's going to improve your arc force and weld penetration. Sometimes it'll improve the fluidity, the wetting action to help spread that puddle out a little more. Sometimes it'll be an easier slag removal. Sometimes it'll be weld spatter amount. Maybe you want as little weld spatter as possible. Sometimes it'll focus on the bead appearance and shape. Sometimes it'll be specific to the weld quality, and sometimes it'll be for the weld positions. So all of these things get taken into consideration in the flux components of your self-shielded or gas-shielded electrodes. And you're never going to get 100% of any one of these things. It's always going to be a balance. But that's why there's so many different electrodes. You may have some that you need really good out of position stability or arc force stability, and so that's going to be the big focus. So the additives in that flux are going to focus on those things, or vice versa. Maybe you're doing a lot of flat horizontal position, you just want easy slag removal and you want a minimum amount of spatter, and so you're going to find an electrode that's got the additives and the components in the flux that kind of cater towards that. So you'll never have 100% of all these things, but you're always going to have a balance that's going to try and cater to what you're trying to accomplish. So self-shielded electrodes like your NR232, a lot of heavy manufacturing, bridge construction, structural steel construction, shipbuilding, and then your gas shielded, very heavy in manufacturing, general fabrication, pressure vessels, a lot of, what people might consider structural stuff, but stuff that can be done kind of in-house because you got that gas shielding, or just thicker fabricated parts, right? Sometimes it's still considered just a fabrication project, even if it's not a structural project, but you're still using heavier materials. And that gas shielded flux core is really efficient, runs real smooth, real easy. So a lot of companies will use that even if they're just a general fabrication shop. A lot of these additives should look very familiar to you, not going to be too dissimilar from what you see in your SMAW electrodes, right? Your aluminum, your calcium. Calcium is one of the bigger components for that slag. So when you're chipping it off, a lot of that is like a calcium deposit that is solidified. Carbon, right? Carbon increases hardness and strength. Carbon is always something that when you add to material, it's going to make it hard, but a little more brittle. The less carbon content in the steel is going to be a little more soft and malleable. Manganese, there's a deoxidizer, right? It's pulling oxides out. Molybdenum increases hardness and strength. Nickel, if you remember from 2A, nickel is one of those things that can be added to get that weathering steel. This helps increase hardness, strength, toughness, and corrosion resistance. All right, so that's one of the more unique things for nickel. You're trying to get corrosion resistance, you'll add a certain amount of nickel in there. Then potassium, your bananas. This helps stabilize the arc and also is used in the formation of the slag. Silicon, right, our solid wire E70S-6, that's got a high amount of deoxidizers, a high amount of silicon in it. This helps pull out those oxides again, and it also goes into forming the slag. Sodium, Arc stabilizer helps form the slag, and titanium, also a deoxidizer, a denitrifier, and helps form the slag. So there's a lot of these things that are dual action. They not only help pull out impurities, but they also help form the slag. And even the aluminum in certain fluxes can be used to, when you introduce that aluminum in the flux, it goes into the puddle, absorbs the oxygen, those oxides, to form aluminum oxide, just like aluminum would oxide out in the atmosphere, and then comes to the surface and becomes a part of that slag. So a lot of these are multi-purpose, they have multiple functions, they're forming the slag, and they're also bringing out impurities or adding strength or helping stabilize the arc. So self-shielding slag system, a lot of magnesium compound. This has a high melting temperature, which is why you'll see the slag kind of re-solidify before the puddle does, because it's got a high melting temperature. So it helps solidify before that weld puddle is fully solidified, and that helps kind of form and shape it. That's also what helps us take it to out of position welding, is that slag kind of forming and holding the puddle as an assist. The compounds in these magnesium compounds are lightweight and fast freezing. Key kind of phrase there, fast freezing, again, allowing you to take these into out of position welds. And then they float to the surface quickly. So they're always rising to the surface and solidifying there, which is, again, how you get that kind of slag coating solidifying before the puddle does. So oxygen and nitrogen can be changed from possible contaminants into chemical compounds. I think we just talked about that. You can introduce oxygen into the puddle, and that will actually pull out some of the oxides and form slag. Some slag components are designed to be more fluid and are ideal for just vertical down. So again, not all position welding electrodes can be used for vertical up. And then other electrodes not recommended for vertical down welding because of that heavy slag. So it just depends on that electrode classification. So the shelf life of mild and alloy steel electrodes is estimated at roughly 3 years. Okay, so that means they can stay inside their box or packaging for up to 3 years. They should be stored indoor, so you want to keep the humidity to a minimum, and then obviously they should be protected from weather or adverse conditions. So we don't sit on our wire, our electrodes very long. We run through pretty much 100% of what we get multiple times throughout the semester, so we rarely have an issue with things sitting too long. At most, they might sit over summer, which here in the valley we have very dry summer, so humidity is not an issue. But typically we're running through these electrodes fast enough that we don't really have corrosion issues on the wire style electrodes. Shielding gas. So obviously the main point of a shielding gas is to provide shielding from the atmospheric contaminants. Usually it's either going to be 100% carbon dioxide, CO2, or a mix of up to 75 to 85% argon, 15 to 25% CO2. So very much the ballpark of where we are for most of our solid wire MIG gases. So again, reactive gases are gases that can combine with the weld pool. These are popular for gas shielding because just like your flux, you're doing more additives into the weld pool. Carbon dioxide is an inert gas that becomes a reactive gas at higher temperatures. I think it's like 200 to 300 something degrees where CO2 becomes a reactive gas. It's also a much lower cost than argon CO2. CO2 is a very cheap gas. So sometimes people will run electrodes specifically because it's very cost effective, right? Doing a gas shielded flux core is already going to be a little more expensive than a self-shielded because you have to run the gas, but CO2 is like the cheapest gas you can run, and it does a very good job. You get that deep and wide penetration profile just like in MIG. If you're not too concerned with things like spatter and noise or appearance, then 100% CO2 is usually just fine. So when exposed, the arc decomposes into carbon, right? So you're just adding carbon into that weld pool. becomes carbon monoxide and oxygen, and then it reacts with the other elements in the weld pool. And I'm sure some of that flux component is going to be those deoxifiers or deoxides, so it's going to pull any excess oxygen out. So 100% CO2, it results in a more erratic, harsher looking sounding arc, right? We call it the harsh arc, and it increases that weld spatter, so it's a little messier, a little noisier, a little more erratic, but it's very cost effective. So usable for or unable to use gas electrodes and spray arc metal transfer made with 100% CO2. So just like in the GMAW process, you need a certain amount of argon in order to do spray transfer. So if you're using a flux cord wire and you're using 100% CO2, you will not be able to do that as a spray transfer process. And then globular metal transfer will work with CO2, and that's used a lot. But most of the time, if you can, you're going to do that spray transfer just from the efficiency standpoint. Remember, doing spray transfer metal mode transfer is the most efficient way to run a wire fed electrode. So same goes for a flux core. If you're using gas shielded and you're running 100% CO2, you cannot spray transfer. You can globular, you can short circuit, but if you're going for the efficiency standpoint, you'll have to use that additional argon to get it to do the spray transfer mode of metal transfer. So when using CO2 and argon, the slag can freeze slightly lower. When using 100% CO2, slag can freeze slightly lower than when using the mixed shielding gases. Many flux core gun electrodes are made to use CO2 as shielding gas, but you should only ever use it if it is specified. So going back to the electrode classification, if you have a C or an M after that second digit, or that first dash number, then you should use the gas that electrode has been designed for. So I'm sure a lot of shops kind of ignore that and get away with it just fine, but just know if it's got that C or M, that electrode is meant to be used with 100% CO2 or a mixed gas. So minimum of 75% argon, so that's why we have that range of 75 to 85. Exceeding the maximum recommended argon can result in higher than expected weld metal tensile strength. Okay, so you may be making the tensile strength higher than it should be if you have too much argon. But the argon, one of the pros of it is it makes a quieter, more controlled arc and a more fluid wet puddle versus that 100% CO2 that's very harsh and very spattery. So argon comes in and kind of helps stabilize that whole arc. So argon compared to CO2 or a mix, 100% CO2 is going to be lower cost because argon's a little more expensive, and mixing the gases takes a little more effort at the filling plant. The penetration profile is going to be deep and broad with CO2. That addition of argon is actually going to make it a little shallower and narrower. Arc transfers really can't do spray arc, more globular. The mixed gas, you're going to get more spray arc capability, which means more efficiency. For CO2, again, it's going to be nastier, it's going to be spattier, it's going to be a harsh arc, it's going to be less appealing to weld. You start doing that spray transfer, it's always going to make a much cleaner, smoother arc. The weld finish is very smooth and clean, no spatter if you've got your settings dialed in, so very appealing. And then less susceptible to gas marks, okay? So when you're running 100% CO2, you have less chance to get those gas tracks, those worm tracks that we talked about in the last unit. Remember, that's just gas getting trapped inside the puddle and rising to the surface, so it's kind of stuck between the surface of the weld and the slag, and it's a little bubble that kind of trails along with you as you're welding, and it makes like a groove in the surface of the weld. And we call that gas tracks, gas marks, worm tracks, a lot of different names for it, but you have less likely you are less likely to get that you're running 100% CO2 versus your mixed gas. All right, guys, that's the end of this unit. So Unit 3 will be next. Thanks for sticking around.